Okay. Right, so thus far, the focus of this course has been on the effect on reaction rate due to the concentrations of the reactants. And I walked you through the analysis of two elementary type reactions, the first and second order reactions, right? And we formulated the rate equation, the rate law for those reactions and solved them. So actually gave an explicit expression for the time dependence of the concentration of a reactant, right? So in this lecture, we're going to concentrate on the other important factor, other important determinant of reaction rates, which is temperature. Now, the temperature dependence we have so far hidden in the rate constant, in the factor K that occurs in the rate law. So this time we're going to elaborate a bit more on that and find out how that rate constant depends explicitly upon temperature. Now, the fundamental model that we shall be the framework basically for our analysis is the collision model, the collision theory model, right? Well, it's pretty straightforward and self-evident almost. If you want molecules to react, first of all, they need to come together, and then in a collision. And that's not enough usually, because what is furthermore required is that there needs to be enough energy in that collision. The collision needs to be sufficiently energetic for the reaction to occur. If not, the molecules will simply bounce off each other, right, and move on their way and get involved in other collisions, which, if sufficiently energetic, may lead to products. Okay, so right, so if we consider this example of a monatomic particle and a diatom, BC, then we can consider this reaction with an atom exchange, right, where the atom B is being picked up by A and C moves off on its own, right? Now, typically, for any reaction, bimolecular reactions in particular, the process passes through what we call a transition state, or activated complex, as it is called, where it is still, well, you have the particles together, but it is still not decided whether or not the products will form, or whether the reactants will remain as they are, remain intact. Now, this is represented typically in the form of a potential energy versus reaction coordinate diagram. Well, the horizontal scale, it's a bit vague, but it's kind of a measure of the progress of the reaction. So you start off on the left with the separate molecules A and BC, and as you continue along that coordinate, which could be something like a distance between molecules, right? As simple as that, but it could be something more complicated. But what it represents doesn't really matter that much, right? And the final stage at the other end of this scale, you find the products A, B plus C, right? We indicate the relative energy of reactants and products by the level, or the vertical level above the coordinate axis. Now, the energy is potential energy. Now, what is potential energy? Potential energy basically is an amount of work that has to be done in bringing together those molecules within a particular configuration. For example, to form the activated complex, an amount of energy is required to force them together. And that is indicated by the ascending branch here of this graph, potential energy versus reaction progress. At the top of it, you have the activated complex. And the difference in energy, potential energy between the initial reactants and the activated complex is called the activation energy or activation barrier against the reaction. Right? And this, so that is the energy required to form the transition state. Of course, that energy has to be available. That has to be stored initially in the form of kinetic energy of the molecules they collide. Yeah, because according to the law of conservation of energy, the total kinetic energy is conserved, but it can be converted into something else, in this case into potential energy, right? But of course that energy has to be available first. If it falls short, then of course there's not enough energy available to climb over that hump and the reaction will not occur. So that is how you interpret this diagram, right? It's more a schematic than anything else, than anything quantitative, right? So the collision energy, which is kinetic energy, initially has to be at least equal to the magnitude of the activation barrier, you know, in order for products to form. Right, so as I was telling you, the energy available in the linear movement of those molecules will have to exceed the potential energy barrier, so the activation barrier. Now, a measure of the average kinetic energy of molecules in, say, in a gas is given by the temperature of the gas. You know? And with temperature, I mean the absolute or thermodynamic temperature, or Kelvin temperature. You know, it can be shown that that Kelvin temperature is a direct measure of the average kinetic energy of a molecule or collection of molecules. And it varies in direct proportion. That kinetic energy varies in direct proportion to the absolute temperature. Now, of course, at low temperature, therefore, the kinetic energy is low on average. So the likelihood of a successful collision, that is a collision between reactants that produces the product species, that the likelihood of that event occurring will be correspondingly low. Yeah, so the higher the temperature, the higher the fraction of molecules that possesses enough kinetic energy for a successful collision increases with temperature, right? So the reaction goes faster at a higher temperature. Again, a fairly unsurprising conclusion. Now, what has been found experimentally for many reactions, that the rate of a reaction doubles when you increase the temperature by 10 degrees. That's just a rule of thumb. It's not a general result, but it just gives you an idea of what the effect of temperature is on the reaction rate through the rate constant, obviously, right? Now, to make this a bit more quantitative, we can consider the distribution of kinetic energy amongst molecules at a given temperature. Of course, not all molecules move at the same speed and have the same kinetic energy. That some molecules will have will move slowly, others move very fast. So you find that molecules distribute themselves according to this what we call Maxwell-Boltzmann distribution. That tells you that if you were to take a snapshot of, say, a gas consisting of molecules, and you were to sort those molecules according to their kinetic energy, then you would end up with a distribution that looks like this. Of course, each individual molecule will continually change its energy, so move from one category into the next, right? But if you consider all of them together at any one time, the distribution will be stationary and will depend upon the temperature. Where at higher temperatures you expect to find more molecules in the high energy region, and you also expect a general shift in the maximum or in the average of the distribution to higher values. Right? So if, in particular for the case of a reactive gas, if you consider pairs of molecules colliding, the number of molecules that have sufficient energy exceeding the potential energy barrier EA, which is given by the shaded area beyond EA, the shaded area under the curve. You see that at low temperature that area is small. That means the fraction of molecules possessing that amount of energy will be low, and it increases with increasing temperature, right? Well, there's an explicit mathematical form for the distribution, so you can actually quantify those fractions. We're not going to do that here, of course. It's just to give you an idea, a qualitative idea of what is going on. Now, sometime in the 19th century, it was observed based on experimental results that for most reactions, the temperature dependence of K follows a particular pattern that was discovered by Arrhenius, a Swedish physical chemist. So the dependence on temperature can be given in the form of a simple formula known as Arrhenius equation, where the temperature occurs here in an exponent, right? But there's also a pre-exponential factor A, which has a weak temperature dependence as well, which is normally ignored. So we will consider A to be a constant. EA is an energy, is the activation barrier, which is expressed here in terms of joules per mole. Right? And that is to ensure that EA upon RT is without a unit. Remember, R is the gas constant, right? 8.314 joules per Kelvin per mole. You multiply that by the absolute temperature of the gas or fluid, right? So you get joules per mole, and that has to be cancelled by joules per mole in the numerator in EA, right? So that is the unit, joules per mole, or typically kilojoules per mole. That is the order of magnitude. Right, so that is the Arrhenius equation, and you see that it has two parameters that are to be determined by experiment, namely the factor A, which should have the same unit as the rate constant K. A is simply a pre-exponential factor, right? We have not interpreted it. It has something to do with the frequency at which collisions occur, right? But I'll say a bit more about that later on. And EA, we already interpreted that. Yeah. Now, just to see why increasing temperature increases the rate constant, imagine T goes up. Yeah? That means EA is always positive, so EA upon RT becomes smaller. Yeah? Now, exponential of minus EA over RT is the same as 1 divided by exponential of plus EA over RT. Right? So you have T increasing, then this EA over RT decreases, and the exponential of plus EA over RT decreases as well. That means that its reciprocal, 1 upon exponential EA upon RT, will increase, which is the expected trend. But now we can actually quantify this. So the aim of kinetic studies that consider temperature dependence is to find the values of the Arrhenius parameters A and EA for a given reaction. Yeah, and right, so you could interpret the exponential factor as a measure of the fraction of molecules that have enough kinetic energy to surmount the barrier EA. There's a subject called statistical thermodynamics that explains why it takes this particular form. It's known as a Boltzmann factor. I don't know if you've heard of it already. Okay, there's a question here. No,
yes, good morning. Can you please explain what A is?
A. Okay, A, well, it's written here. It says it's the frequency factor of the exponential factor with the same unit as K. And it is a measure of the number of collisions that occur per second within the gas.
So it's not a constant, it's different for each reaction?
It's, well, it is roughly a constant. It does show a weak temperature dependence, which is normally ignored. So we will consider it to be a constant.
Okay, thank you.
All right. Right, so the exponential factor is a measure of the probability that a given pair of molecules, as they collide, have enough kinetic energy to form the product. Yeah, and that obviously is proportional to the rate of the reaction. That the larger that fraction is, that exponential, or that probability, the more product you get in 1 second. So the faster the reaction, in other words. Okay, now just to go a bit deeper into the matter, let us, since you have now completed a course on thermodynamics, let us try to find something like a rationale for why that Arrhenius law looks the way it does. So consider the following process: a reaction, a bimolecular reaction between A and B, forming a product C. Now, each chemical process is in principle reversible. Now, if you look at the potential energy diagram, you see that you can cross that hump, the energy barrier, from left to right, but also from right to left. Even though going from right to left, the barrier is a bit higher, right? But each chemical reaction, in principle, reversible. So we can define a rate constant for the forward-going reaction, from A to B leading to C, but also for the back reaction, right? Now, if you have these compounds A, B, and C present in a closed vessel, so that none of them can escape into the atmosphere, then eventually a chemical equilibrium will be established, where the rate of the forward reaction is exactly matched by the rate of the back reaction. Yeah? So equilibrium here doesn't mean that nothing is happening, it's just that the rate at which C is being formed in the forward reaction is equal to the rate at which C is being lost in the back reaction. So the concentration of C, and hence of A and B, remains fixed in time. This is what you refer to as a dynamic equilibrium. An old physical-chemical equilibrium, also between phases like liquid and vapor, these are dynamic equilibria. Now this process you have studied from the point of view of thermodynamics. And you came up with a criterion for equilibrium, which is that in that reaction mixture with A, B, and C, the Gibbs energy of that mixture should be at a minimum for there to be equilibrium. Now that translated into the following expression in terms of the standard Gibbs energy of reaction, the delta G naught, and that, well, Dr. Nelson has explained that to you, what that means. In equilibrium, that should be equal to minus gas constant times the temperature of that mixture times the logarithm of the equilibrium constant. The equilibrium constant in kinetic terms can be defined as the ratio of the forward and reverse rate constants, Kf upon Kb, right? So if you make K the subject of this equilibrium condition, which is what we know as the law of mass action, then you divide through by minus RT and then take an anti-log, right? And that gives you this. So minus delta G naught upon RT and the anti-log thereof equal to K. K also being equal to the ratio of Kf and Kb. Now, if you concentrate on this second form, Kf upon Kb equals that exponential, that suggests that the individual Ks, the Kf and the Kb, may be expressed as in a similar way, also as exponentials. So Kf we can write for that exponential of minus a delta G, which we write as delta G for the forward reaction, and then with this symbol, the dagger symbol or activation symbol upon RT. Similarly for Kb, right? But with a different delta G. And we can also multiply it by a factor, a common factor C, just to make it a bit more general, right? So that if you divide Kf by Kb, that C will cancel out and you end up with this, provided that delta G naught is equal to the difference between this delta G, the delta Gf, and the delta Gb. Yeah, dividing this by that means the exponential of minus delta Gf minus minus is plus delta Gb. Yeah, if you equate that to the delta G naught, you end up with this as the relation between delta G forward and delta G backward, and the standard Gibbs energy of that reaction. So that is just a reasonable hypothesis, right? Okay, now again we can represent this in a diagram. This time we plot the standard Gibbs energy of A, B, and C against the reaction coordinate, which we denote by Q. So a measure of the progress of the reaction. So we start off with reactants A and B, right, which are present at a certain standard Gibbs energy level, G naught. Then they pass through an activated state, AB dagger, right, before moving downhill to the product side, right? Now the activation barrier in this case, the barriers are the delta Gf and the delta Gb that we just defined, right? And you see from this diagram very clearly that the difference between the two, so this height minus this height is negative because this is higher than the other, gives you the standard Gibbs of the reaction, of the overall reaction, so the difference between AB and C. Yeah, and the delta G naught is negative, indicating that under these conditions, the reaction from going from left to right will be spontaneous and eventually reaches an equilibrium. Yeah, because the concentrations of A and B decrease, that of C increases. That means that the forward rate decreases and the rate of the back reaction will gradually increase until the two are level, right? At that point you have an equilibrium. All right, so this was our hypothesis. So a rate constant, K, can be written as a pre-exponential factor, C, whatever it is, times an exponential factor, which contains the negative of an activation standard free energy or standard Gibbs energy upon RT. Now, the definition of Gibbs energy is well known to you at this point. It is defined as G equals internal energy plus pressure times volume minus temperature times entropy. And what entropy is, well, you have some idea of that again at this time. So our delta G here can be written as a sum of these terms. Delta G equals delta U plus P delta V minus T delta S, where the delta U, delta V, and delta S here pertain to the process of forming an activated complex out of the separate reactants. Now, internal energy, if we focus on this term here, internal energy is always a sum of kinetic energy, well, which is stored in the linear motion of molecules and also in their rotation. And there is a potential energy term as well, which relates to the interactions amongst molecules. Now, the kinetic energy, the difference in kinetic energy between the activated complex and the separate parts, the A and the B molecules, we know to be directly proportional to temperature. Whereas the potential energy difference between the activated complex and the individual molecules A and B is by definition equal to the activation barrier EA. Right? So that is internal energy. It's something proportional to temperature plus something that is temperature independent, the activation barrier. The next term in delta G is P delta V. Well, P delta V is only significant if there is a change in volume occurring upon forming activated complexes. Now, that change in volume is negligible if it is a reaction in liquids, so solution reaction, so we ignore it. If it's a gas phase reaction, then you would have to consider the change in the number of molecules that occurs upon forming activated complex out of A and B. In this case, that would be -1 because you go from 2 molecules to 1, and multiplied by RT using the ideal gas equation of state. So something again proportional to T. Then finally, T delta S also contains a factor T, highlighted here, and delta S we assume is independent of temperature, right? So if we combine all of this, all those three terms, you notice that there are 2 or 3 terms that are proportional to temperature, and we lump them all together into a single term, B times T, plus a temperature independent term, which is activation barrier EA. So that is what our delta G, what the temperature dependence of delta G looks like. Now let's go back to our Arrhenius form here, or Boltzmann factor as it is. There we divide delta G by RT, so we do the same thing here. Yeah, that takes us there. You see that divided by RT cancels this T here, so you get B upon the gas constant, which is now temperature independent, and EA upon RT. So now we have the temperature dependence here. You then plug this delta G upon RT back into K, so we minus it, take an antilog, yeah, and then split the exponential into a constant factor, which is the exponential of B upon, or minus B upon R, and the temperature dependent factor, which is exponential negative EA over RT. So if you now combine the constants here, the temperature independent factor, C exponential minus B upon R, and you call it A, right? What you get is indeed Arrhenius, right? So this here provides you, well, it's not something that I would ask you about in an exam, but this is just for your information, right? Just to hopefully this will make you feel more confident in working with the Arrhenius equation now that you've seen where it comes from, right? Yeah. So now having established this, let's go back to the rate expression. Okay, the question is if A is temperature dependent. No, it's not, because C is independent of temperature and so is B. So all of this stuff here, which we call A, is temperature independent. Yeah, the entire temperature dependence occurs here. You see? Good. All right, so now let's go back to the rate law. It's a binary reaction. No? Two molecules, A and B, involved, so the rate of the reaction will be proportional to their respective concentrations. And the constant of proportionality is our K, which we can now write out in more detail. So A times the exponential factor, which we call a Boltzmann factor, right? So the what is here in front of the Boltzmann factor is in fact the frequency factor. This is a measure of the number of collisions that occur within unit volume in unit time between A and B molecules. Yeah, so it is the pre-exponential factor in Arrhenius law times the product of the concentration of A and B. Of course, the higher the concentration of A and of B, the higher the frequency, the greater the frequency of those collisions will be. So that makes sense, right? Yeah, so this here gives you the total number of collisions per unit volume in unit time. But of course, it's only a certain fraction that will be successful in forming products, and that fraction is given by this Boltzmann factor. Now, that is how you interpret the rate law using Arrhenius law in this way, right? Okay, now there we have it again. Now to analyze experimental data, what you normally do is to bring this Arrhenius law, which looks a bit awkward mathematically, bring it to a linear form, and you do so by taking logarithms on both sides. So you get the log of k here equals the log of a times the log of the exponential. Of course, the ln cancels the exponential, so you are left with minus ea upon rt, which is an expression that is more easily analyzed quantitatively, right? Because it suggests that the ln of k depends in a linear fashion upon the inverse temperature, right? So what you do if you if you repeat an experiment a certain number of times at different temperatures, you determine the rate constant at each temperature, then take the logarithm of k for each value and plot it against the inverse temperature. Right? What you expect to find is a straight line with a negative gradient, yeah, that is equal to minus the activation barrier. Remember, EA is always positive, upon the gas constant R. So from that, you then from the slope, you then obtain the value of EA, as minus the slope is the gas constant. And then from the intercept, yeah, so the value at 1 upon t equals 0. From that intercept, you then obtain the logarithm of A, and you take the exponential of that, and you have A. So the two Arrhenius parameters can be obtained by plotting your data in this form. Now here, in this graph shows you what qualitatively what the trends will be for reactions in which you have a low or a high activation energy. A low activation energy means a small gradient. Yeah? High activation energy. Okay, there's a question if you were to carry out the reaction under similar conditions with the same reactants. Yes, you would. You would repeat the same experiment using the same initial concentrations, but just at different temperatures, right? I've already shown how you could, for simple reactions at least, how you could obtain the rate constants. So if you repeat that procedure at different temperatures, you get a number of k values at different temperatures, which will then enable you to construct this graph, this plot, ln k versus 1 upon t, which you then proceed to analyze to find the Arrhenius parameters, the A and the EA. Right? So for high activation energy, the graph will be steeper, obviously, and the sense of the variation with temperature will be stronger than in this case. So the reactions with high activation energy are more sensitive to variations in temperature. That's what it tells you. Okay. All right. Now, suppose that you have done the experiment at only 2 temperatures. That in itself would suffice to find the Arrhenius parameters, because you would have 2 equations. You have 2 values of k at 2 different temperatures, and you have 2 unknowns, namely the Arrhenius parameters A and EA. Right. So in principle, you could then solve the resulting Arrhenius equations, right, rather than drawing a graph, which is not really necessary. You just get 2 points and you draw a straight line, but the quicker way is just to solve, in that case, to solve the problem algebraically, right, using the method of solving simultaneous equations. So suppose that we have at one temperature T primed, we determine the rate constant. We determine it as K primed. And at a different temperature T, we find it to be equal to K. Then we write out the Arrhenius equation for each, right, in the linearized form. So in the logarithmic form, like that. And then proceed to find the values of EA and A. Now, the way to do that is to combine the 2 equations by subtracting them, subtracting the second from the first, for example. You do that on the left-hand side, you get the ln of k primed minus ln k, which is the same as the ln of k primed upon k, right? If you do the same thing on the right-hand side. You see that you cancel the ln A. Right? This is gone. And you're left with minus EA upon R T primed from this. Minus minus is plus EA upon R times T. Right? Then you simplify this. So you cancel the ln A's. EA upon R is a common factor of these two terms. So you place them outside the bracket. Inside the bracket you get minus minus is plus 1 upon T. This minus 1 upon T primed. That. No? So this is if you have only 2 data points. This is the recommended procedure. So all you need to do now is to substitute T and T primed. So you evaluate this factor. This one is also known because you know the K primed and the K. So this is a number here. R is the gas code. Hence, you find EA from that. Okay, well, once we have EA, then you can go back to either one or the other of the original Nernst equations. You substitute the EA that you just found. Say for the T primed, where you know the K primed. So everything there is known except ln A, which you then calculate from there. And it should be the same value whether you use this equation or the other. So that is how you find the 2 Arrhenius parameters in that case. Okay, so I see we have gone through all the slides now, so still have some time left. Let me stop the recording first.